to study the equations, the formulas, you see, which lays at the base of the turbomachinery. And today we will study the last and most important equation which we need to know to study of working process of the turbomachinery. So let's share the screen for Ahmed. Okay. So 1 second. Okay, let's continue. Sorry. From the theoretical mechanics, you know the equation of angular momentum, and you know the law of conservation of angular momentum. So I hope you are studying it. As far as I remember, theoretical mechanics, it's study at this course. So from theoretical mechanics, you know what resultant of all forces which acting on the body with the mass m, which are moving with the speed c, and spaced from the x of rotation by distance r, creates torque about the axis of rotation. It's the formulation from theoretical mechanics. And this equation from theoretical mechanics, I hope you are already studied. So, like at previous case, like at previous equation, we will apply this equation from theoretical mechanics to the flow in turbomachinery. So, let's study why it doesn't work. Let's study the random turbomachinery. In reality, it's not very big important what kind of the turbomachinery we will study. In my picture, it's the centrifugal compressor. And we will make the same things like in the case of the continuity equation. We will split, so of course, during receiving the equation, we will think what we know everything about the flow in the inlet, and we know everything about the flow and at the outlet. We know mass flow rate, density, temperature, velocity, flow angles, every information about the flow in the inlet of our channel and at the outlet of our channel. So let's split all flow, all big continuous flow, to a great number of small tubes. So this is example of the flow tube. Of course, in reality, the flow tube which we will investigate smaller than flow tube in the picture in, I think, 100 or maybe 1,000 times. In reality, it's very small tube. Maybe we couldn't see it. The tube so small, what we could to say, what the parameters in the cross section of the tube have the uniform parameters. So what I want to say additional, we are not taking into account supplying or extracting of mass flow rate between the inlet and outlet cross section of the small tube. So at the first period of the time, at time equal 0, the tube was in the position 1, 4. So it's at the time equal to 0. So after very small time period dt, which leads to 0, the tube are moving into the position 3, 2. It's at the time equal to 0 plus dt. Okay. The time period dt, so sorry. so small, what we could to say what the parameters between the section 1 and 3 and 4 and 2 are the same. So by other words, the time so small, then the flow comes from the position 1 to position 2, the flow parameters doesn't change. And the same about the outlet section. What we could do say additionally about this flow, what the parameter, what the flow tube 3, 4 doesn't change. It's the same for the two cases. So, do you understand what I mean? So we have tube, and after small time, it's moved to the other position. And we have the common part of these two tubes at which flow parameters doesn't change. So let's apply this equation to this case. Could you apply this equation to this case?
Sorry?
How to apply it?
Apply which?
Equation to formula to, I don't know. So you need to write this formula to this case. How to explain it? How to write this law to this case? It's, of course, in reality, it looks difficult. It's really so, and I think, and for me, it looks difficult. But if we a little bit think, we will find the simple decision.
So where is d divided by dt?
It's differentials. So, but I think it's not important at this moment. So we need to write this equation for the first position of the tube, and after that write to the second position. But let's think. If we look to our tube between 3 and 4 are not moved. It means what the angular momentum doesn't change during the time which we investigate. That's why we could to avoid from our investigation flow tube between the 3 and 4. So we could to not investigate this part because nobody changed during the time which we investigate. And for us, we need to write this equation to this mass and to this mass. So it means what we need to write how the angular momentum at this value are changed for this mass and for this mass. If we look to the first small part of the tube, you could to see what at first moment of the time it was here, it was present, and after time dt it's disappear, because what we have in reality, at first moment we have tube, at last moment we have tube like this. We could to represent such action like what we have tube 3, 4, and at first time of first period of the time this mass comes in, and at other period of the time it's dropped from outlet part. So at first moment we have this mass, at the second moment this mass are disappear. And about the outlet part, it's at first moment we have no this, at the last moment it's disappear. So that's why finally we write this equation for the first time and minus angular momentum at the last time. But at the last time we have no this mass, and that's why it will be only angular momentum for at first position of the time, at first moment. And about the last volume, the same. At first moment we have no this mass, that's why angular momentum are equal to 0. at the second position of the time, we have such angular momentum. That's why the equation will be simplified. We are only write the angular mass momentum for the inlet mass at the first moment and minus angular momentum of outlet mass at the last moment. So what we will do, we remember what the mass divided by time, it's the mass flow rate. And that's why we replace dm to dt to mass flow rate. After that, we comes from differential equations to the normal equations. We are multiplying all parts of this formula to omega. It's angular momentum. Oh, sorry, angular rotational velocity, which are measured in radian per second usually, or maybe degree per second, and divided all parts to mass flow rate. I don't see to mass flow rate. What we are receive. Let's erase all elements. Could you say what is it? Angular momentum multiplying to the torque. Do you know what is it?
No.
I not clear understand here.
We know it. We take it before. We know it by Arabic. We take it in Egypt. We take it in the thermo. We take it in the hospital.
What is the value we receive here? You could to meet it at other subjects, at other courses. It's the power.
Okay.
Power. If we will divide power to the mass flow rate, it will be power which produced by 1 unit of the mass. By other words, it will be specific work. So finally, the left part of the equation will be specific work. So, okay, the next simple question: could we replace something at the left part of the equation? Could you see something which you know at the left part of the equation?
Anything?
The part is the inlet flow of the coil.
Which flow you mean?
The left part.
At the left part, it's yes, it's the changing of angular momentum. Yes, but you could to simplify this equation. If you remember one formula from school courses.
Because we use another letter.
So
I think it can be 1 meter minus another letter, but it will be 2 and the second it will be 1.
no, so it's not very convenient. I don't know why it's moved so much. So do you remember omega angular velocity multiplying by air? It's equal circumferential velocity. So if you remember the rotational velocity, it's the velocity here. It's used in the school course of the physics, for example. So that's why we could to simplify this equation, what specific work equal to such formula. These equations are very useful in the theory of the turbomachinery, and By other words, this formula are called Euler equation for the turbomachinery. It's really very useful in the turbomachinery courses, and I think maybe 80% of this course based on this equation. So if you need to analyze working process of the turbomachinery, first moment which you need to do, you need to write this equation. And I think in most cases you will find the solution of your task, deal with the turbomachinery. Okay, let's try to find this equation from other position, and after that we will try to discuss some conclusions, some consequences from this equation. So we at this equation we are speak about the momentum, about the torque which are created around the rotational of about the axis of rotation of the turbomachinery. How do you think, what the source, what the reason of creating of the torque? What are creating the torque in the turbomachinery? How do you think? So we are speaking about the momentum. What are creating the momentum? What are creating the torque? Pressure. Good trying, but not exact. So what are usually creating torque? Of course, force. Yes, you have some distance, and you have some distance r. You are applying force, and this force create momentum. Yes.
Can we say energy or only force?
At this moment, we speak about the force, because force initially will be source, first reason of appearance of momentum, and we will discuss what kind of forces create momentum and how to calculate it. So the source of momentum, source of torque, it's the forces. Of course, it's in our case, in the case of the turbomachinery, it's the forces which impact to the blades. And how do you think, what kind of forces are impact to the blades? I think it's very simple. It's two kinds of forces. It's the gas forces, because you have the blades and working fluid flow around the blades, and you have some forces because you have interaction between the blades and the flow, and finally you have some resulting force, and it will be this one, gas forces. It's force which appears at the momentum of how to say interaction between the blades and the flow. We are discussed with these flows at previous lectures. These forces. So these gas forces, it's the forces which appears as results of interaction of blades and the flow. And of course, these forces finally create the torque, because your blades have the round shape, and the blade locate at some distance from rotational axis, and that's why you apply force to the blades which are not laid on the axis of rotation, and that's why blades could be moved, because you create the torque. It's the first moment. You could calculate this force using such formula. We will not look carefully to this formula because this formula comes from aerodynamic. And as far as remember, this formula called Zhukovsky equation for the lift force. It's like for the wings. We are use the same relationship like for the wings to calculate the lift force of the gas forces which impact to the blades. Without detailed information, we are find this force, this one, this is gas forces. And if we know forces, if we know radius, we could to calculate the torque which are create this force relative to the rotational x. And in common case, especially in the case of radial turbomachinery, we could to achieve Coriolis force. This is one of the kind of the inertia forces. It will be important in centrifugal compressor, in centripetal turbine, but it's not have great influence in the axial turbomachinery. But we are speaking about the common turbomachinery. That's why we are taking it in account. So you know what is Coriolis force.
How is it reduced the gas force that prevents
So it's very interesting problem. You don't know what is the Coriolis force. This is one of inertia forces which are impact to the moving elements, and these force are normal to the direction of relative velocity and direction of x of rotation. How to explain it? For me, it's very hard to explain what is Coriolis force, but you must to study it in the in the theoretical mechanics. If you will try to remember theoretical mechanics, if you try to read theoretical mechanics lecture, maybe you will better to understand this force. Unfortunately, I'm not clear remember the physical mention of this force, and I hope what you have some knowledge from theoretical mechanics about it. So, but from theoretical mechanics, you must to remember, I hope, this equation. It's equation which help to you to calculate Coriolis force. And if you know force, if you know distance between the point of application of the force and x of rotation, you could to create the torque which are produced by Coriolis forces. So we have only two kind of forces, and that's why to calculate assume torque we need to assume these two equations, and we will realize it. And finally we are receive two relationship for calculating of the torque. So it's very interesting. It's mix between the Russian indexes and English indexes. I am very wondering. So we are do the same thing like this, the previous equation. We are multiplying all elements to the angular velocity. At the left part, we are receive specific work like in previous case. And at the right part, we are receive such equation, such relationship. And so maybe if we will speak about the axial turbomachinery, in the axial turbomachinery, the radius of the flow doesn't change. In the axial turbomachinery, we have the blade, and the flow comes approximately at the direction parallel to the x of rotation. That's why inlet radius and outlet radius will be approximately the same, and that's why first term will be leads to 0, because I hope you understand what circumferential velocity, it's the radius multiplying to angular momentum, and if the radius are constant, the circumferential velocity will be the same, and first term will be leads to 0. And that's why the equation for the specific work of axial turbomachinery will be simplified. So what we are doing at this moment, we are find two equations.
You mean like U1 and U2 is the same also, right?
Yes, for how to say, for axial turbomachinery, U1 will be equal to U2, and that's why we could to extract it from our equation. So what I want to say, we receive two equations, two formulas for the specific work of the turbomachinery. One from the position of the force at this slide, and at previous slide we received the second equation from the position of the equation of angular momentum. Of course, we receive the same specific work. It means what this equation, this formula, and this formula could to calculate the same thing, and that's why we could to make it equal. So, and we unit these two equations at one equation. That's why finally we receive two equations, one for compressor and one for the turbine, which could be called equation of angular momentum for the turbomachinery. By other words, it could be called Euler equation. But in reality, when we speak about the Euler equation, usually we mean this part. But you could use this part too. Sometimes it's useful for the calculations. And for the case of axial turbomachinery, we discuss what for axial turbomachinery U1 equal to U2, and we could to extract circumferential velocity from our equation. We receive simplified shape of this equation for axial turbomachinery. And from this equation, we could to find for the case of axial turbomachinery, this difference, and this difference will be equal. It could be used in real practice. So what else? Typically, during some talks, during some explanation, we could to not use the name Euler equation, but maybe in worldwide practice, it's used Euler equation, but in Russian practice, we simply say U multiplying by delta Cu. And the guys which deal with the turbomachinery usually understand what you mean. So, we receive the equation of angular momentum, by other words, it's Euler equation for the turbomachinery at this moment. And I think it's the most important equation for the turbomachinery. Be careful here. It's most important equation for the turbomachinery. Okay, let's try to apply this equation, and let's try to receive some important conclusion. Before we will discuss it, I want to pay your attention at one moment. What is LT? LT? No, it's specific work. At this case, we will use letter L Of course, you are correct. What we are use letter L to designate length. But usually, if we will speak about the length, we are use small letter L. Here, specific work. But what kind of the specific work? Because I think maybe it's for the students it will be hard to understand at first moment. But in reality, we have a lot of specific works in the turbomachinery. We have supplying specific work. We have specific work which are supplying to the flow. We have work of how to say ideal compression, work of ideal expansion. We have a lot of specific works in the turbomachinery, and of course it could be hard to you to understand it, especially at the first moment. And for better understanding of this equation, you need to remember what this specific work, it's the work which are how to say, supplying using blades to the flow or extracting using blades from the flow. By other words, you have the blades, and this specific work, it's the specific work which are on the blades. Do you understand what I mean? Because the energy which are conserved inside the flow, it's one value. The energy which you are extract from the flow, it's other value. Energy which you are transferred to the compressor, it's the third value. It's because we have losses at each step. For you, it's the most important idea here. You need to understand what this specific work, it's the specific work which are on the blades. You are extracted from the flow or you are transferred to the flow, this energy using blades. And looking to this equation, let's try to find some conclusions. First conclusion, the specific work which you are supplying or extracting from the flow using blades are depend only from two things. It's depend only from circumferential velocity, and it's depend from the differences of circumferential projection of the flow. It's really important idea. The specific work which you are extracting or supplying from the flow depend only from these two things. What it means? For example, it means what this work are not depend from the temperature, are not depend from the.
Think about you. Think about you.
Yes. 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 You are correct. Yes, you are correct. It's depend only from you and from the differences of circumferential projection of velocity. But for example, students and not students, maybe as engineers, very often thinks what the specific work which you are supplying or extract depend from the temperature. In reality, it's not depend. They think what it's could be depend from the pressure difference, from the properties of the fluid, from the moon phase, from the, I don't know, your health at this moment. It's not depend. It's depend only from two things. It's the first idea. The second idea, if, for example, if we speak about the turbine, the expansion energy, the energy which you are received during expansion process, depend from the temperature and pressure ratio. And for example, if you realize huge pressure ratio or maybe big temperature in the inlet, you could to receive very big value of energy inside your flow. But if your rotational velocity small or turning angle differences of circumferential projection of the flow are small, you couldn't extract this energy from the flow. That's why I say to you what it's very important to understand what this energy are energy on the blades, because energy inside the flow and energy on the blades, it's the two different things. Yes. The next conclusion, it's the strange conclusion. It's a really strange conclusion, but sometimes you could to use it, especially students could to use. Let's imagine you have the black box and you don't know what are inside, but you know the relationship between these two values. It's really very strange situation when you don't know what is it, but you know the circumferential velocity and circumferential projection of absolute velocity. But let's imagine this situation. If you know relationship between these two terms, you could to say what are inside. If this value more than this value, it means what you are supplying mechanical work at this device, and it means what it's compressor. If you have opposite picture, what U1 multiplying by C1 U more than you are received the turbine. It's really strange situation.
Well, I think we take it also in the ceremony.
Maybe, I don't know, but as far as I know, these moments are not very useful in the thermodynamic courses, because it's especially turbomachinery things, and
He told us not also very important.
Maybe.
And it not came in all equation, and it's very more less than 1% can come.
It could be, but it's not typical. How you could to use this information? I'm going to give to you the calculation, and maybe if you will find at your calculation what you are calculating turbine, but here you have less, it's mean what something wrong. It could be mark what you make mistake. It's typically you are receiving the turbine the opposite sign. If you have
the opposite sign to be compressive.
Yes. If you calculate the turbine and you have sign less, it's indicate what you have the mistakes usually.
It's not cheap.
Conclusion, it's maybe more. It's more, maybe it's more example. So, of course, usually we want to increase specific work. It's very typically we want to more power, more specific work. How to increase the specific work? Look into this equation. We have two ways. We could to increase. How we could to say? Okay, I will return back here. Specific work, it's the circumferential velocity multiplying by delta C. Wait, we have some problems. Where is it? So we are moving very slowly. This one. Oh, we have forgot about the maps. Okay, I hope he seen our presentation. Okay, we want to increase specific work as usual, and specific work could be calculated like U multiplying to delta CU. And how to increase it? Of course, we could. Perfect. Okay. And how we could to increase U?
Need U.
Yes, two ways.
You can make CU less.
No, no, no. We are
Maybe
speaking about only U. About only U.
power torque.
About only circumferential velocity. Today we are discuss what U is omega multiplying to angular velocity. That's why. No. Angular velocity multiplying to radius.
If you can increase radius or
Yes, perfect. You could to increase radius and you could to increase no, it's omega.
It's like me.
Yes. And it's depend from rotational speed. Finally, you increase rotational speed. So we have one interesting example. It's a local example from Kuznetsov company. How the rotational speed influence to the specific work of the stage and influence to the construction. So we have two gas turbine engines, NK36ST and NK37ST. Initially, it was aircraft engine NK32. It's a three-shaft bypass engine with afterburner. And it was for military aircraft, but maybe 30 years ago, it was converted for the ground application. The afterburner, nozzle, mixer,
supersonic.
yes, for supersonic bombers, but initial engine was modified for ground application. The bypass was closed. The low pressure compressor was modified. One stage of the low pressure turbine was removed. Nozzle, afterburner, and mixer was removed. And this part was taken mostly from initial engine NK32, and this part are called gas generator. And at the outlet part of the engine was mounted three turbine, which are connected with the energy supply system. If we look to these two engines, if we look to the parameters of these two, we are fine. What these two engines, from their point of view of the thermodynamic, the same, because they are produce the same power, they have the same mass flow rate, they have same pressure ratio, they have same temperature before the turbine. If we will look to the free turbine, from the position of the thermodynamic, it will be the same turbines. It's really the same turbine because same pressure ratio, same mass flow rate, same temperature, same power. If you will use thermodynamic calculation, it's really not difference. What's the difference between these two engines? The difference in application. The NK36ST are used for the driving of gas pumping unit. NK37ST are used to drive electrical generator. And rotational speed of the three turbine are determined by the device which are supplying energy. That's why rotational speed of the rotor of free turbine determined by gas pumping unit, and typical rotational speed of gas pumping unit approximately 5,000 rotation per minute. 5,600 rotation per minute. It's typical values for the gas pumping unit. Rotational speed of electrical generator typically 3,000 rotation per minute, because 3,000 rotation per minute correspond to electricity with 50 Hertz frequency. What I want to say additionally about these turbines. these turbines have the same sizes, same diameters, because this part of the construction really the same, and outlet part of gas pumping station and electrical generator station use the same detail. That's why the diameters of the turbine the same. What it gives for us? It's give the next moment. What here we have rotational velocity 500 rotation or 5,000 rotation per minute. Here we have 3,000 rotation per minute. It's mean what in the case of NK36ST, the circumferential velocity will be much higher because rotational speed are more. And it's mean what the specific work which you could to extract using one stage are higher and NK36ST. And finally, you receive what the same power in the case of NK36ST with the higher rotational velocity, you receive using 2 stages. Here you receive the same power using 4 stages. In my case, it's very wondering example because really the same engines with the same parameters and difference only at one number. You have difference only in only on rotational speed of output shaft, and it's make great differences in the construction. So you see here 2 stages, here 4 stages. I'm very wondering because
And the two is more rotating?
these have more rotating. Here 5,000 rotation per minute.
So
Here 3,000. Because here rotational speed are lower, specific work based to this equation are lower, and you couldn't extract produce big specific work at one stage. That's why you receive the same power using more stages.
it depends for stages. يعني if we have more stages, it will be less or no? Or what?
No, these 2 turbines give the same power, but if you will reduce circumferential velocity, you are reduce specific work per one stage, and it means you increase number of stages. So, in my opinion, it's very interesting example. And you see what in reality rotational speed of the free turbine rather low. For example, as far as I remember, rotational speed of high pressure cascade approximately 15,000 rotation per minute. And you see what we have big difference between the diameter of the gas generator and the 3 turbine. Why? Because if we are if we are increasing radius, we are increasing specific work. If we keep the same diameter, we are receive not 2, not 4 stages, maybe 6, maybe 7 more stages. Of course, more stages, more expensive, have more mass, and have other disadvantages. That's why it's really very typical for the engines which are converted from aircraft to the ground application. So it's example of Russian engine, but you could find example of Rolls-Royce engine which are converted for ground application. They have the same geometry approximately. So the next conclusion. So if we look to this equation, if we look to this formula, we could say what if you want to create specific work, if you want to create power, this term must be not equal to 0. So if this term will be not equal to 0, it means what the specific work not equal to 0. By other word, if you want to extract or supply mechanical work, you need to what this term not equal to 0. It's mean what It's mean what you need to turn the flow.
So not to be 0?
Yes.
So, W1 not to be equal W2?
Yes.
And
yes.
U not to equal 0?
Yes. If we are looking to the velocities, this is relative velocities in the inlet of the rotor wheel and at the outlet of the rotor wheel. If W12 not equal to W22, it's mean what the vector of W will be turned. By other word, to create an energy exchange between the blades and the flow, we need to turn the flow. We need to change the direction of the flow inside the blades. And how to explain to the flow what it need to turn. You couldn't say, hey, flow, turn to the 30 degrees. It doesn't work. That's why you say set you create special elements which turn the flow, and that's why we will speak a lot of about the blades. Why we need to use blades? Blades turn the flow. The main idea of the blades turning the flow, because the turning of the flow, it's the main instrument of the energy exchange between the flow and the blades. So, okay, let's look carefully. If we speak about the compressor, if we want to supply mechanical work, this value must be more than 0, and finally we could to receive what W1 must be more than W2U. It's clear, I think.
Yes.
If we look,
Cannot be 0 or minus. It can't be minus, right?
if you want to supply work to the flow, like in the compressor, it could be like here. It couldn't be 0, of course, because if it's equal to 0, you are not receive the specific work. And if it will be negative, you will extract work in the compressor, but you are not receive pressure ratio, finally. That's why you need to provide such relationship. If we look to the direction of the vector W1, it could be realized if beta 1 will be less than beta 2. You see, beta, it's the angle between the front, between the circumferential direction of the circumferential velocity and direction of relative velocity. So, and if we look to the turbine, we need to provide other relationship, W2U more than W1U. At this case, you will extract energy from the flow. And if we look to these vectors, we could to find what vector, we could to receive such relationship between the projections of the velocity if we provide beta 1 more than beta 2. At this case, WU will be more than W1U. So, the final conclusion of this slide, what for the compressor, beta 1 will be less than beta 2, in the turbine the opposite picture. Let's a little bit speak about angles. How to realize it, what we are finally receive. If we will analyze the cross-section area of the flow in the compressor with the such relationship between the angles, finally we are receive what the relationship between the cross-section area in the inlet and at the outlet depend from relationship between the sinus of the angles. And because beta 1 less than beta 2, we are receive what this relationship will be less than 1. And it's mean what the channel between the blades of the compressor will be diffuser. So in the compressor, to organize energy exchange, we need to organize diffuser channel between the blades. I remember to you what the diffuser channel have one big disadvantage. The flow very often separate from the walls in the diffuser channel. It's a big disadvantage of such channel. Of course, you could to avoid this disadvantage if you will make not so big diffuser factor. So usually you know cross-section area at the inlet and at the outlet. And you could to realize this diffuser using different way. You could to make such a diffuser, or you could to make such diffuser. This is the same cross-section areas. At this case, if you have short diffuser, you are receive flow separation and a lot of losses. It's not good. So if you are reducing length of the diffuser, you are increase the losses deal with the separation of the flow. But if you will increase length of the diffuser, you are reduce the probability of appearance of the separation, and you could to find the way you could to break the flow without the separation. But long distance, it's the long friction. Long losses deal with the friction. That's why finally you have some optimum diffuser factor, because you need to find the good combination between the separation losses and between the friction losses. So typically this angle of opening of the diffuser, I think 16 degrees. It's typical value which allows to you to break the flow without the strong losses, without the separation. In the turbine, the opposite moment. The relationship between the cross-section area more than 1, and it's mean what the channel between the blades of the turbine have the diffuser shape. The diffuser shape have no such problems, and you could to realize any confuser factor. Oh, sorry, confuser channel have no the problem with the separation, and it's really good advantage of such type of channel. So, if we return back to few minutes. You could to see what the difference between W1U and W2U will be depend from the differences between the beta 1 and beta 2. So by other words, value of delta WU, which have strong influence to the value of specific work, will be depend from the flow deviation angle, delta beta. So it's the angle to which you are turning the flow in the blade row of the compressor and in the turbine. And of course, we are always want to increase this value. It's because we want to increase specific work. How we could to increase it? From one hand, of course, we could to increase circumferential velocity, but from other hand, we could to increase delta WU. And how we could to increase? We could to increase angle delta beta. So, and let's look how the increasing of delta beta influence to the shape of the channel in the compressor. We are fix outlet angle and we are reduce angle beta 1. And it's initial shape of the compressor channel, and this is shape of the channel of the compressor of this increasing delta beta. And if we look carefully, if you are turning the flow, if you are increasing delta beta, you are increasing diffuser factor. So finally, you are replace this diffuser to the diffuser with the more angle. This angle, it will be alpha 2. This angle will be alpha 1. Alpha 1 will be less than alpha 2. But if you will increase this angle, you are increase the probability of the separation. And finally, you are increase this probability of increasing losses. That's why it is not good idea to strongly increase delta beta in the compressor, because finally you are receive great value of losses. For example, you could imagine what you could receive separation here. This is the high probability. From one hand, you have diffuser channel. From other hand, you are turning this channel. That's why the probability of the separation of the flow at this moment will be very high. And if you will turn the flow at much angle, a big angle, you are receive big losses. That's why value of delta beta are limited. Usually not more than, you want to ask something? Usually not more than 30 degrees. Okay, at the next slide we are discuss how it's influence to the construction of the engine. In the turbines, we are using confuser channel, and in the confuser channel, we have no problem with the separation. That's why we could to turn the flow to any angle which we want. But of course, we have some limitation deal with the, I don't know how to say it in English, but we couldn't realize some angles. For example, we couldn't realize angle 130 degrees. We couldn't realize it. What it means? It means what we are turning flow to the opposite direction. It looks strange, then the flow will be tuned to...
And also 360.
Yes, of course, but that's why we have no limitation, but some angles couldn't be realized in real practice. That's why here, angle delta beta less than 30 degrees, in the turbine we could realize angle 130 degrees. So it means what, because we have no problems with the separation in the confuser channel, flow deviation angle have no limitation. Only limitation deal with the construction. And of course, finally, it leads what in the turbine stage we could realize more value of delta W, and finally we could to receive very big delta W. So let's continue. Okay, let's skip this slide. This information will be more interesting. So what we are finally have? Finally, this is flow. I forgot what to say. This is velocity diagrams for the compressor stage and for the turbine stage. In the compressor stage, the delta beta angle are limited by the diffuser factor. In the turbine stage, we have no the limitation of this angle. That's why finally value of delta W and delta Cu in the compressor stage is rather small. In the turbine, because we have no limitation, these values are big. And what we could to say, if we have approximately equal circumferential velocity in the compressor in the turbine, the specific work of the compressor stage will be less than in the turbine stage. And what it means? The turbine stage produce huge specific work, but one stage of the compressor could not supply it because we have limitation. Of course, we could try, but it finally leads to huge losses and efficiency of your engine will be poor. And that's why we couldn't supply all energy which produce one stage of the turbine at one stage of the compressor. And how to solve this problem? To use several stages of the compressor. And that's why typically number of stage of the compressor greater than one stage of the turbine. So, and it's really typical what we have 6, 7, 10 stage of the compressor and which drive by 1 or 2 stage of the turbine. It's really typical. So, and I think it's a very important conclusion because it's explained why the gas turbine engine looks like we know. Likes the number of stage of the turbine less than number of stage of the compressor. So, and you could to study the engines in the pictures, you could to study the engines in the engine museum. Typically, you find this relationship. For example, this is Trent 900, I think, engine. Maybe not clearly seen, but we have one stage of high pressure turbine which drive approximately 7 stages of the compressor. Perfect, like usual. One stage of intermediate pressure turbine drive 8 stage compressor, like usual. But if we look carefully to the bypass to turbofan engine, we will find some strange moment. As far as I remember, 4 stage turbine drive only one stage of the fan. It means this moment doesn't work. It's a really interesting moment. For high pressure cascade, for intermediate pressure cascade, and for low pressure cascade of the turbojet engine, 1-2 stage of the turbine drive a lot of stage of the compressor. But it doesn't work for the low pressure cascade of turbofan engine. Why? The main problem what the mass flow rate through the fan and the turbine are not the same. So let's try to explain. If we are connect compressor and the turbine, it means what the power of the compressor equal to the power of the turbine. Of course, we have some losses between it, but we will neglect it. We could to write the power like specific work of the compressor multiplied by mass flow rate through the compressor. And the same for the turbine, specific work of the turbine and mass flow rate through the turbine. But if we will look to the low pressure cascade, we will find what the mass flow rate rather small at the turbine, because only G1 comes through this turbine, and through the fan comes all mass flow rate through the engine. And if you know G assume equal to G1 multiplying to the bypass ratio plus 1. So what it means? It means what in the fan we have the same power like in the turbine, but we have huge mass flow rate, but small specific work. That's why we could to realize it using 1 or 2 stages of the fan. In the turbine, we have small mass flow rate, same power, and it means what we need to realize huge specific work. That's why we couldn't, very often we couldn't realize it at one stage. It's clear. I think it's important conclusion because it's explained why the engine looks like we know. maybe it's not really simple to understand it, but in reality, it's not very hard. So, and of course, I think it's the most important conclusion. So, of course, we have short time and we need to stop. But today's lecture was very important. From one hand, we are explaining why the engine looks like we know. It's from one hand. And from other hand, the Euler equation are very useful. It's really used very, very often in the turbomachinery course, and I think it's the base knowledge in the turbomachinery theory. And as I say before, if you need to analyze something in the turbomachinery, first what you need to do, write Euler equation. So I think that's all for today. If you have any questions, you could ask. I will discuss with Professor Dima about you, because you say one moment, he say other moment, and today I don't know.
But in any way, you win the Russian finish. The Russian
ones.
before the New Year, right?
Before, I think before the New Year, maybe right after New Year.
Yes, we can. I can take my exam at 12. In the 12 December. 12 December.
Mm-hmm.
It's okay. It's only 10 days or something like that because I must go to Egypt at 14. If the airport work in Egypt, if they say they will close the airport after 1 week in Egypt, sure I will go after 3 days, 4 days to make the coronavirus paper and.
Okay, I understand. Okay, I will think how to solve it more.
And if I can take more things, if you want to send it to me, a lot of things in the mail, and I will study it and make notes. Okay, it's for me.
Perfect.
If it have mails, it's okay.
Perfect. Окей. Чего ты останавливаешься? Блин. I couldn't stop this guy.